Welcome back. This will be the first lecture in a series of lectures that deals with transport in electrochemical systems. We'll introduce a mechanism that is of relevance here, which is called the migration. So just to put things in context, we started this series of lectures on thermodynamics of electrochemical systems. We addressed a variety of topics. All the topics that we discussed were involved equilibrium in electrochemical systems, and using that we came up with certain quantitative relationships. Moving on from equilibrium thermodynamics, we want to look at two kinds of non-equilibrium effects in electrochemical system. The first non-equilibrium effect is that of charge transport across the electrode-electrolyte interface. Again, this is a non-equilibrium system, so we want to develop a rate expression for quantifying such a non-equilibrium transport. Here the transport is that of charge across an electrode-electrolyte interface. So we derived, again, certain quantitative relationship, and we elaborated how they can be measured in experiments and the central equations underlying electrochemical kinetics. In this lecture and a series of next few lectures, we'll be looking into another non-equilibrium effect in electrochemical system. This involves ion transport. In this case, this involves electron transport, but this involves ion transfer and ion transport. And the central equation here is the Nernst-Planck equation, which we will look at in the next lecture. But the central mechanism which we'll present in this lecture is that of migration. This qualitative thing will lead to this more quantitative equation presented in the next lecture. So, as I said, there are two kinds of rate processes. So there are some species in the bulk. They're transported to near the electrode, and there is a charge transfer. This we addressed in the last few lectures. And then a reduced species gets formed, which gets transported to the bulk again. We had looked at the driving forces that are behind the transport, which is the concentration difference. Okay, there is a concentration difference between the bulk of the electrolyte and electrolyte near the electrode surface. This is the reason for transport of species here, in this case indicated by O and R. Okay, so we had looked at it in a manner, in a qualitative manner first, and then we had utilized mass transfer coefficient to discuss this transport. But we would look at this entire system of transport and electrolytes in a more quantitative manner in the present and the next few lectures. So we will, before we move on to electrochemical systems, we will review some of the notions which you might have already seen in transport and chemical systems. We'll first define some terms and then elaborate on, briefly elaborate on the underlying equations in chemical systems. So the first term which we want to define is called the flux. So for defining the flux, you consider a cross-sectional area. Okay, so the number of ions is dn transported per unit time per unit area. All right, so that is, and the units are mole per meter squared per second. Right. This transport flux depends upon gradient in concentration of the species. Finally, the reason for this law, that's a more fundamental reason for this law based on irreversible thermodynamics. Using chemical potentials, we can see why this form of law is valid. But when Fick's demonstrated these effects, or it could have been called Fick's observation instead of a Fick's law, because it's not as fundamental as Newton's law. But in any case, what was demonstrated was that flux is proportional to gradient in concentration. This would be a negative number, but flux is a positive number, positive quantity in this direction. So to accommodate the negative quantity here, you have a negative sign here, which will give rise to a positive flux. The proportionality constant is the diffusion coefficient. All these things must be familiar with you from your previous classes. This flux is given with respect to the average molar velocity, right? So you can also give this flux corresponding to a fixed frame of reference. In this case, the overall flux would be this flux, which is given by this equation, times convective velocity. Okay, so the convective velocity with respect to fixed frame of reference is V, bulk velocity. So the overall flux will be the diffusive flux plus contributions from convection. Moving on, we want to be, so just to emphasize, this is, there is nothing changing with time. There is an element of time here because the flux, number of ions that are transferred per unit time, but this is will also occur at steady state. That is, if there is a concentration gradient, let's say, and there can be a steady flux. Okay, so this flux need not be varying with time. This can be a steady state flux if a constant gradient that exists in the system that can give rise to a steady state flux in the system. This is often referred to as a Fick's first law. The flux can also change with respect to time. Let's see how that occurs. Okay, so you typically consider a shell, and you do mass conservation within this shell, right? There is some amount of material that gets into this shell, and there is old amount that is present in this volume. There is influx and outflux of material. So the new amount which is present in this shell depends upon what was already present and what is coming in and going out, right? So if you do this balance, this is the volume of, this is the concentration that is present in the system, volume of the system, this cross-section area, this kind of mass balance you must have done in your previous classes. Such a mass balance will give rise to what is called the Fick's second. So the concentration of the species changing with time can be correlated to this particular differential, okay, the differential of the flux with respect to X. Incorporating the expression for flux, you will get the Fick's second law. Dou C by dou T is equal to diffusion coefficient and the second gradient in second differential of concentration. This is the Fick's second. Again, this you must have seen it in your previous classes. Just go and refresh it in case there are such uncertainty, or we can discuss these issues during the discussion. So here, what we have considered is a planar surface wherein the cross-sectional area is not changed. Okay, so the change in concentration, even though concentration changes with time, that is mainly due to differences in influx and outflux of material. there can be another reason why concentration can also change, that is dependent on the geometry of the system. For example, if we are not looking at a planar cross-sectional area, if the cross-sectional area of this element itself is changing, you can also have a change in concentration with respect to time because of changing cross-sectional area. So this is an important effect. Often what we might have seen, we would consider is diffusion from a spherical source. So the system will have spherical symmetry. In this case, there's a particular relationship which you might have seen in your previous classes. All these things is just meant to be a revision of what you must have seen in your previous classes on mass transfer. So you can come up with this kind of relationship. This is often we will use this expression in certain future lecture. Okay, so this is geometry. This geometry, spherical geometry, is quite important. So you should just become familiar with the effects of geometry on fluxes. Why that is important? Because this A appears at the denominator. So just changing the geometry will give rise to changes in the fluxes. How do we couple chemical reaction to transport? Supposing you consider a bulk reaction. So in the previous 2 slides, we looked at influx and outflux of chemical species, right? So there can be another reason why the species can disappear or appear. That is due to chemical reaction. This can this can easily be accommodated within the framework of mass balance. There is a disappearance of species A because of forward reaction that is taken into account in this term, and there can be appearance of species A because of the backward reaction that is taken into account in this term. So all these things, the balance was made in 1 dimension. All these things can be extended to 3-dimensional system. Again, you just these are simple mass transfer in certain element. In this, it was a 1D element, this 3D element. You just do accounting in this volume element. What is coming in all 3 directions, and how much the concentration is changing, to what extent it is changing. Okay. All these things can be incorporated succinctly using equations of this form. Again, this is the reaction term corresponding to something like this. Okay. So you remember this fluxes can be not just the diffusive flux, it can be flux in a fixed frame of reference. We can incorporate this n into this, and we can write a quantitative equation. With just there's no fundamental law here. All we are doing is just we are taking into account mass conservation. Okay, just careful accounting gives rise to these laws. Nothing more to these laws. We will now come to the central mechanism that is of relevance to electrochemical systems. We'll introduce a term called mobility. Okay, we'll connect it with what you've seen in the past. So mobility is defined as the average velocity of an ion in n particular electric field. So let's think through this and connect it to what you've seen. Okay. So for example, if you have a sphere falling under gravitational potential in a medium, okay, so the gravitational potential will tend to accelerate the sphere, but there is a resistive force offered by the medium. Okay, so under the balance of these 2 terms, that is the effect of gravitation, which tends to accelerate, and the effect of the medium, which tends to retard, the velocity, you will attain, the sphere will attain a terminal velocity. That's a steady state velocity attained by the sphere. Okay. So in effect, the similar intuition can be extrapolated to our system here. Okay. So the electric field will tend to accelerate the ion, therefore the velocity, you may think that it's going to keep increasing. The velocity will be increased because will continue to increase because of electric field, which is not true, because when the ion moves in a viscous medium, the solvent that are present in the medium will offer resistance, and that will retard the motion of the ion. Okay, so balance of this can also give rise to terminal velocities. In effect, we are going to define mobility as the average velocity per unit per electric field. Okay, so for this, to implement this equation, we need to have an expression for velocity. That you can relate it to Stokes' law. Again, this you might have seen in your previous class in transport phenomena or in fluid mechanics. The Stokes' law is given by velocity is the force per divided by these terms, right? This is the viscosity of the medium. This is a measure of the retardation, the resistance offered by the medium is incorporated via this particular term. This is the R of the ion, the radius of the ion. The force on the ion is given by the valency times the elemental charge times the electric field. Okay, this is just from elementary electrostatics. You can get this divided by this particular term. That will give you the velocity of the ion in the medium. This is a good model, especially if you take into account waters of hydration. This R we are referring to, it is not an ionic radius which you see in inorganic chemistry. What is of relevance here is the radius of an ion surrounded by waters of hydration. Okay? So you can have some very counterintuitive numbers here. If you look at the ions in the same column but of different rows, as you go down the row, you may see a decrease in radius. Okay, that's because of the water of hydration decreases. So, in effect, without going into such details, what I'm trying to insist is this is a pretty good model if you can incorporate waters of hydration, and after incorporating waters of hydration, you have to document RI, right? This is a good model for most of the ions, and where this is really not, it doesn't capture the details is in the case of hydronium and hydroxide ions. Okay, transport that you see in these kinds of systems. Okay, to explain this, Grothus proposed a mechanism. I want to emphasize that these were done in the early days of electrochemistry. Okay, so look at the year. Okay, this was in 1806. So this was around the time of Faraday and so on. Okay, so a lot of ionics research in ionics was done in 1800s. So this is one of the important results. And what is fascinating is in those times, there was no quantum mechanics. Ions could not have been visualized quantitatively using experimental tools. All the imagination occurred just in the mind. Okay, so with this, Grothus proposed an interesting mechanism that is of relevance to these kinds of systems, not of relevance to other cations and anions, but for just where hydronium and hydroxide ions are involved. Grothus mechanism is of relevance. Okay, so why you see very high transport is because it is not an ion that is shuttling from across the medium. Okay, so what is happening is just a local transport. Okay, so this ion can get transferred, and the next ion, it's not this ion, the other ion, this ion can get transferred. Okay, so there is just a local transfer of ion. If you have the field direction in this manner, the ions will get transported here. Likewise, in the case of hydroxide also, there is a local transport. Okay, if the field is in this direction, the ion transport occurs locally. Okay, so it is just in the next event might not be the transfer of this ion, it might be the transfer of this ion. Okay, so there is just a local movement of the ion which gives rise to an effective transfer of ions. Okay, so that is the reason. I've just in a minute I'll try to summarize the Groth's mechanism, but this is quite complicated, and a lot of quantum chemical calculations have been done in the last 10-15 years to understand the Groth's mechanism. But at least you should be aware at this level that the transport involving hydronium and hydroxide is more complicated, doesn't fall into this picture. Okay? So more molecular picture has to be adopted if you want to look at the transport in these systems. So again, Kohlrausch did a lot of research in this area, and what he noticed was that in the limit of infinite dilution, the mobilities he measured was a constant, okay, because there is no ion-ion interaction. Okay? But as the concentration increased, there was ion-ion interaction. So the mobility at different concentration has to be modified, taking into account the effect of concentration using ionic strength. This was something that was defined in some previous lecture. Ionic strength is defined using this particular term. And the effect of concentration can be incorporated using this term. And the mobility at different concentration can be expressed using this expression. Okay, so this expression was empirically obtained in 1800s using by Kohlrausch, and more molecular reasons for why this term exists was provided by Onsaga. Okay? So a lot of research again has gone into understanding the mobilities. It not only depends upon the concentration, it also depends upon the counterions that are present, because all these things will go into the ion-ion interaction. Okay? But in the case wherein all these things are simple is when the concentration is very less. In the limit of infinite dilution, you just get a constant. Okay? That is indicated by UI naught. So having introduced mobility, we will see how that's going to help us in obtaining fluxes in electrochemical system. The mobility was defined in this manner. We elaborated how you can get VI using certain formula in the previous slide. The fluxes is given by velocity times concentration. Right? This is per unit area. So this is just how you would define, let's say, flux in a pipe. Okay? You would have defined fluxes in a pipe by taking into account the velocity times the cross-section area, right? In a similar manner, you can define the fluxes, ion fluxes, using these two terms, the velocity times concentration. The dimension will also is correct. So once you have the velocity from this expression, you can define the migration flux in the following manner. Electric field is given by differential of potential in the electrolyte. So putting this equation along with this equation gives me the migratory flux of ions in the electrolyte. Okay, so the electric field is defined using the potential gradient that exists in the electrolyte. All these transport mechanisms are of relevance to ion transport in the electrolyte. Overall, just to summarize what we have elaborated in this lecture, we looked at qualitatively what kind of mechanisms that are relevant in transport of species in an electrolyte. Okay, so when the transport occurs because of some electrochemical reaction at the surface of the electrode, right? Because of which that a concentration gradient is generated, which gives rise to transport. Then we went on to define certain important terms. You have to look at these terms very carefully. We first defined fluxes, and the fluxes can vary not only because of changes in input and output fluxes, it can also vary just because of the geometry. We define the fluxes at a particular point in this, let's say, this cross section, at this interface, let's say, using the concentration gradient that is present at that interface, right? So that is the Fick's first law. You can also have changes in fluxes because of changes in concentration gradient, which gives rise to Fick's second. All these things are to do with chemical transport in chemical system without any electrochemical potential being present. All these things will be of relevance. Okay, so but what is of particular relevance is a new mechanism that comes because of the potential that is present in the system. Okay, so see, these diffusion fluxes exist in electrochemical system. This is not absent. Okay, so these fluxes exist because of concentration gradient. On top of these fluxes, you have a new mechanism, additional mechanism, which is the migratory fluxes. That, to quantify that mechanism, we introduced mobility and then connected mobility to fluxes using the velocity that are generated due to the coupling of the ion with the electric field. Once this is well defined, you can define the migratory flux in the following. It is given by the mobility of the ion, concentration of the ion in the electrolyte, and the potential gradient that exists in the electrolyte. So potential gradient coupled to the ion gives rise to migratory fluxes. The concentration gradient gives rise to diffusion fluxes. And of course, there is an additional term because of the convective flux. When you put all these three terms together, you would see the Nernst-Planck equation, which will be the topic of the next lecture. Thank you.